Welcome, everybody. I suggest that we wait a few minutes more until more people have joined us. So let's wait a few minutes. Welcome to everyone who's joining us now. At the moment, we have about 40 connections. We want to wait a little bit more to make sure that as much people can reach us as possible. So let's wait until 35, 3 more minutes. Thank you for your patience. I didn't do it. Okay, well, let's get started. Maybe more people will join us along the way. Maybe you want a word, Thiago?
Okay. Good morning, everybody. Thanks a lot for joining this initiative with the webinar. It's the first time we're doing it in this format with YouTube, and we will try to make it work the best we can. We have organized it such that you can interact with us through questions, so don't hesitate to write all your questions in the chat. We have some experts in the room that will try to answer. We could not cover, of course, everything in this format, but whatever questions we cannot answer here, we'll try to address it with the relevant people afterwards. I want to tell you that this initiative is also because in ESA, we have been working a lot on space debris mitigation. This is an aspect that has affects quite a lot our future missions, and that we are trying to implement these new guidelines very seriously. And whatever we have learned in this exercise, we would now like also to bring to a very wide community that is building up in Europe, that is working on nanosats and CubeSats. So we want to share our knowledge with you and start a dialogue that can then go on afterwards. So I'll pass the word now to Njord. My name is Thiago Soares. I'm working on Clean Space as system engineer, mostly on these aspects of space debris mitigation and all the technologies for larger satellites mostly. And Njord has been doing this exercise of involving you and also addressing the potential solutions that could also be exploited in smaller satellites. So thank you, and I pass you the floor.
Thank you, Thiago. So I think my colleague told you quite a lot about the goal of this webinar. So my name is Njord Eggen. I'm pleased to welcome you today to this event. We are quite excited to see how many people are involved in this, how many people we've managed to catch the interest of. So with this, I'd like to welcome all of you to this webinar on CubeSats in the context of space debris. I'd like to thank my team for helping me out on this. And as my colleague said, you will be able to ask any question that you might have throughout the live stream. You can just send it in the chat, and one of my colleagues will pick them up and either answer them on the spot or forward it to me so that we can answer them at the end of this live stream. So without further ado, let's get into it and let's look at the presentation. All right. So I'm going to describe the goals in a little bit more detail in just a second, but just for you to see the agenda, up to 10:45 roughly, we will be presenting to you, and then there will be a Q&A session where we will be able to answer or discuss around the questions that you might have. So the webinar goals, what do we want to do today? First of all, we will introduce you the team Clean Space that is presenting this webinar. And why we're organizing this. I believe that my colleague said quite a lot about this, so we will be quite brief. We will introduce the space debris problem, and we will present the guidelines that have emerged as a consequence of this space debris. And finally, we will discuss technologies that may be helpful for CubeSats to be compliant with guidelines. Now, keep in mind that we're going to discuss potential approaches. We are not providing a ground truth or solutions that might be applicable in any case. And finally, we would like with this event to close the gap between ESA and the CubeSat community. As my colleague said, we have focused mostly and we have experience with larger satellites, but we haven't been so much involved with smaller satellites yet, and we believe it's an important thing to be done. So let's get right into it. What is Clean Space? Clean Space is a team which encompasses three main disciplines. There is eco-design, which aims at assessing the environmental impacts of space missions and trying to promote greener technologies. There is CleanSat, which aims at designing spacecraft such that they will not have a negative impact on the growth of space debris. And there is active debris removal, which is the design to, like the name implies, remove large pieces of debris from the space environment, or alternatively, try to perform in-orbit servicing. Today, we're focusing on CleanSat. The reason for this is because we believe that the CubeSat community is a major actor for the sustainability of the space environment of tomorrow. So we are trying to involve the community more. So let's look at space debris. Space debris encompasses orbital debris and the re-entering objects, so objects that are soon to be removed from the space environment. Now, the definition of orbital debris is somewhat involved. I'll give you that much, but let's take a look at it. So orbital debris is defined as any man-made Earth-orbiting object, including fragments and parts thereof, which is non-functional, with no reasonable expectation of assuming or resuming its intended function, or any function for which it is or can be expected to be authorized. Like I said, this definition is somewhat involved, but let's try to take a look at what it means. What we're talking about is objects that were created by humans that are in orbit around the Earth and that are unresponsive, that are not communicating data on their potential attitude, and that are non-cooperative, that are not responsive to commands. Now, it's important to know that the human-made space debris environment is largely dominated by the space debris environment is largely dominated by human-made objects. Except around millimeter sizes. Below that size, there are more meteoroids. And we will see what these different sizes mean in a while. So if you look at the graphs on the bottom, you can see that there's a significant amount of objects with a size above 0.1 millimeter. Only a tiny fraction of those, which is still a significant number, 900,000 objects, are larger than 1 centimeter. Out of these, you can see that there is still a smaller fraction yet. That is a small fraction that is tracked objects and cataloged objects. These are mostly objects with a size above 10 centimeters. And yet, out of these, there is only about 6% of operational satellites, which means, in brief, that all the rest, the 94% remaining, is basically trash. This goes on to tell you the situation, because we're now talking about the cataloged objects. That gives you an idea for the other objects that are not cataloged with a size above 1 centimeter. Now, where are these objects? These objects are mostly in low Earth orbit, so with an altitude up to 2,000 kilometers. This is one of the protected regions, along with the geo region. And you might see here that there are two sudden increases in the number of debris. The first one was caused by an anti-satellite test in 2007. The Chinese launched their tests and successfully destroyed one of their weather satellites, which increased the number of trackable objects by 34%. This is not talking about objects that are not trackable with sizes smaller. In 2009, so 2 years later, there was a collision between an active satellite, Iridium, and a defunct Cosmos satellite, which further increased the trackable object population by 17%. Now, where do these debris come from? There's three main sources that can be identified. There are launches, obviously, what we launch into space, so the rocket bodies that have been used to send into orbit objects. There are the payloads that are at the end of mission that are left there. There's mission-related objects, such as covers that were used to protect lenses during launches. Then there are fragmentations, so explosions that were caused by stored energy on board that has not been depleted, and collisions, such as the collision I was just mentioning in 2009. Finally, there are non-fragmentation debris. These are debris that are created with the aging of materials mostly, so the surface degradation because of the space environment, some particles from solid rocket motors. And the positive side of this is the sinks. There are two of them. The first one is the natural decay, so the use of the atmospheric drag, the solar radiation pressure, and other perturbations that contribute to causing space debris to re-enter the atmosphere. And then there is the active removal, so performing maneuvers that help re-enter the atmosphere, and also non-propulsive maneuvers with passive devices. So let's look at the atmospheric drag to help us as a sink. So the atmospheric drag is our best ally to mitigate the growth of the space debris environment. But its effectiveness is really reduced at higher altitudes. Actually, as you can see on this graph here, there is, at the top of this graph, you can see the orbital lifetime average for objects at different altitudes. Now, keep in mind that these numbers are not representative of each and every object that you might launch, because this orbital lifetime depends on your ballistic coefficient. But it gives you an idea. You can see that below 600 kilometers, generally speaking, your object will remain into orbit for less than 25 years. If you increase this altitude by 200 kilometers, you might stay up to 100 years. And the severity of this increases, obviously. And as you can see, there is a high concentration of objects around the altitudes, which will take a significant amount of time to re-enter. So what causes fragmentations? We talked about one of the sources of debris that were the different fragmentations. Now, the data on the left is slightly outdated because there's been a few more incidents, but it's a good illustration to show that there's a large proportion that we are not aware of what caused this fragmentation. We just don't know. There's several others that are deliberate. The example also is the Feimyun anti-satellite test in 2007 and other deliberate destruction of satellites. There is the propulsion. This is when propellant tanks maintain some of their propellant inside, and this can lead with time to some explosions that completely fragment in a catastrophic way spacecraft. There are the collisions that we mentioned, and there are batteries. Batteries also that can lead in a bad environment, they can lead to fragmentations. Now on the right, you can see also on the fragmentation, the resulting fragments from events. You can see it that between 2005 and 2010, there is a huge spike. This is again caused by what I mentioned earlier with the anti-satellite test and the collision between Iridium and Cosmos. And in recent years, you can see that there has been more incidents due to electrical reasons. So the batteries that might have caused fragmentations if they are not passivated at end of life. I will describe what passivation means in just a while. So let's take a look now at the different sizes and what they mean. The tracked objects are mostly objects with a size above 10 centimeters. These are going to destroy your satellite or have a very high likelihood of doing so if they collide with you. But these are mostly tracked, and we are able to predict their position in time and able to alert different operators of the risks, and so that they may proceed with collision avoidance maneuvers. Now, the most dangerous region is the one that you see between 1 centimeter and 10 centimeters, where you're very likely to cause a loss of your mission and a consequent fragmentation that will cause a lot of debris. And yet we have close to no data about these objects. We just know that they're there, but we have no way of predicting where they're going to be. Below this size, between 1 millimeter and 1 centimeter, we are at the shielding threshold. So this is a hazard for your missions because you might well lose some of your subsystems due to this. So the penetrations and structural damages are very likely. Below 1 millimeter, you have surface degradation. So this is less critical, but with time, this can damage your mission. Now, hypervelocity impacts. Let's take a look at why a piece of object 1 centimeter is relevant. You can see here that this was a hypervelocity impact test with a sphere roughly a little bit more than 1 centimeter that collided with this block of aluminum with a velocity of 6.8 kilometers per second. Please note that this is actually an optimistic test in the sense that it shows you the velocity used for this impact is suborbital. you might reach velocities, relative velocities in orbit for collisions of up to 14 kilometers per second. So the damage might be significantly higher. And this is for objects of the size of 1 centimeter. And as you can see on the graph on the bottom that I recall from a previous slide, you can see that there is a significant amount of such objects into orbit that we are not tracking, not cataloging, and we're not unable to tell operators reliably where these objects are. So I want to show you the consequences of collisions. So this is the Iridium Cosmos collision in 2009. And here you have the collision. And at first you will see that the debris is very fast scattered in the orbital plane of the respective orbits. You can see that this occurs actually quite fast. And with time, with more time, you can see that there is what we call null precession. So due to the shape of the Earth, this debris is not only scattered along the orbital plane, but it is also the orbital plane of the different debris also shifts. So this debris is scattered all around the Earth. Yeah, the situation does not get better. So why is it a problem? Why are space debris a problem? Well, because our modern life now depends on the uninterrupted availability of our space infrastructures. We have the communication satellite, Earth observation, meteorology, and a variety of different missions that we have made ourselves quite dependent on. And the more the space debris environment increases, the higher the chances are that you will lose your mission. And like I said earlier, a debris as small as 1 millimeter can already jeopardize your mission, and a debris with a size above 1 centimeter has a very high likelihood of causing a catastrophic fragmentation and loss of your mission. This is critical because that's one thing that really shocked me the first time I got into this, is what is called business as usual. This is the worst case scenario. When we predict the space debris environment, the growth of it in time, we talk about business as usual for the worst case scenario, which goes on to tell you that the practices have a long way to go before we can have a sustainable use of space. And if we continue the way we're going right now, some orbits will become unusable. So this will threaten a lot of space activities. Now, I want to show you what this business as usual means. This is quite an early prediction before the emergence of new space. So there might be actually more objects if the attitude of the various actors is not sustainable in time. You can see that the environment, in the beginning, it started quite slowly with collisions. What you see in red is fragmentations. And you can see that in the beginning, it starts quite slowly, but then the rate at which these collisions occur is significant. You can see how, you can see that the rate of collision is really increasing fast. So why does it involve you? Why does it involve the CubeSat community? Well, because as you can see, there is a significant increase in the years to come and the years now of the number of objects launched into space, into low Earth orbit. And this is in large part due to the emergence of new space and smaller satellites. You can see that this trend is expected to increase in the years to come. So this is not just a temporary spike. So this is why we believe it's important here in clean space. We believe it's very important for us to involve the CubeSat community and raise awareness. So, okay, this is the most involved slide that I have here, and I ask you to bear with me for it because I think the message is quite strong and important. But I understand that it might be a little bit intimidating when looking at it first. So these are predictions from NASA. You can see the paper at the bottom. You will see, I will provide all of you with the presentation later on, so you will be able to access the various links that were presented. But for now, let's focus on the graphs that we see. These are actually quite optimistic estimates because it assumes that there are no launch failures, no explosions due to stored energy, and that collision avoidance is present during the operational lifetime. And it uses predictions for the next 200 years including and excluding the emergence of CubeSats. So the black curve that you can see on both graphs represents the predictions using historical data for launches of objects before the emergence of CubeSats. The other curves, the green, the blue, and the red one, include also CubeSats, but CubeSats perform different, have a different attitude with regards to space debris, and you can see that this leads to quite a different number of objects into orbit. So both graphs tell you about the number of objects with a size of more than 10 centimeters into orbit between 600 and 1,000 kilometers. Again, this is using predictions, so this is not ground truth. But okay, the graph on the left shows you what happens when with a 60% rate of post-mission disposal. I will explain a little bit more about post-mission disposal, but in short, post-mission disposal, as the name implies, is the sustainable disposal of your satellite after its end of life and removing it from the protected region. So the black curve on the left assumes 60% rate of success, and on the right it assumes 90%. So you see that the situation is slightly better. Now, the blue and red curve are just slightly different. One of them, the blue one, has satellites injected 50 kilometers higher from the lower threshold, so from 650 kilometers. But what is interesting here is the green curve. The green curve is the sum of the historical data for large satellites and the smaller satellites with sizes, the smaller satellites, the CubeSats. And the large satellites have a 60% rate of disposal on the left, while CubeSats do not dispose at all. On the right, it's the same, but with a 90% probability of success. As you can see, if CubeSats do not comply and do not attempt to have a sustainable behavior, there will be a significant worsening of the situation into orbit. The blue and red curve assume that CubeSats and large satellites perform post-mission disposal. So you can see how important it is right here. So let's take a look at the space debris paradigm. So if we look at the definition for these two words, we can look at space debris we defined earlier. So the man-made objects into Earth orbit and the fragments of such objects that are either re-entering or in the Earth orbit, like I said, and that are non-functional, so they do not perform any useful task. And then we have what the word mitigation means. Mitigation is to reduce the severity of something. So what we mean with space debris mitigation is that we're trying to reduce how painful, how severe the space debris environment is for us. The goals of this are to preserve outer space and the environment so that future generations may be still able to use useful orbits, and thus to prevent what is called as the Kessler syndrome, which is the cascading effect which will lead to random collisions occurring everywhere, and that will make these orbits unusable. And then we want to reduce the risk of damage to property, so satellites into space. We want to reduce the pollution to the environment and the risk of it occurring, and we want to reduce also the risk on the ground related to re-entries, because as the number of objects in orbit increases, these objects will also later on re-enter the atmosphere. And these have a risk to injure people. Now, this is very relevant for larger satellites too, because they can have a large number of objects. So we will not focus on this today. So let's take a look at these guidelines now. Now that we've defined what the goal of these, the space debris mitigation, what this means, let's take a look at one of the most widely adopted standards for it, the ISO 24113. So it states that you should prevent the release of mission-related parts during your nominal operation, from accidental breakups, and especially from your intentional destruction of property. You should perform collision avoidance if your satellite is not in an orbit that has a natural decay time of less than 25 years. You should perform passivation. So this is either depletion of the stored energy on board, so from your batteries and from your propellant tanks, or making them safe. Making safe implying that you have to actually demonstrate that you make it safe and that it will not lead to fragmentation. This is very important for long deorbiting times. And then we have the post-mission disposal that I discussed slightly earlier with 90% reliability. Now, this means that you should, for geosatellites, these should be disposed either into a graveyard orbit or somewhere where they will not be in the protected region. And for LEO satellites, this means that such satellites must vacate the region within 25 years of their mission too, of their mission end by re-entering the atmosphere. Now, you can see a few stars here that relate to comments at the bottom. The first comment is on the reliability. The new standard that is still a draft, so do not take it again yet as ground truth, but this is the direction in which we are headed. The new draft coming in 2019 state that there should be a probabilistic assessment of successful post-mission disposal and that this probability should remain above 90%. This standard also states that the orbital lifetime of a satellite should be lower than 25 years from the injection and not from the mission end if you don't have the capacity to perform collision avoidance. Now, this is important to note. And also, these guidelines state that the casualty risk related to each satellite and each object re-entry should be limited to 1 to 10,000. Again, I'm not going to focus so much on this today, but it's important for you to know that it's there. Importantly, these guidelines can be adopted by states, and actually most spacefaring nations have adopted these guidelines, and some of them have enforced them onto their industry themselves. So depending on your location, you might be legally bound to comply with them. This depends on your location. You can find these guidelines you can find documents. I will provide the slides once again. So how can CubeSats adopt a sustainable behavior? Well, first off, there is the orbit selection. You can limit the altitude of your satellite to ensure that the re-entry will occur within 25 years after end of life or from the injection. This is related to the space debris mitigation requirements. You have to use the orbiting technologies if your orbit is not naturally compliant because of drag. So you can use propulsion, drag sails, tethers. You might consider such technologies. Again, we're not presenting them as ground truth that will ensure your compliance. We're just here to discuss what is being investigated. So if you're not in a naturally compliant orbit, which means that you will not re-enter within 25 years, you need to have the possibility to perform collision avoidance. So this requires you to have propulsion. You should aim at passivating the energy sources on board of your satellite. So if you do not have propulsion, you should, like a lot of CubeSats, you should aim at disconnecting your batteries from solar cells, discharging them as much as possible, and avoiding extreme temperatures by design. And you should be able, if you're not capable of performing collision avoidance, you should remain trackable by remaining the information to different entities that relay such information and help alert various operators in case of a potential risk. So here is something is very important. There's a difference that might not be well known between being trackable and being observable. And I would like to point this out because I think this is of major importance. So being trackable and being observable are two different things. Indeed, we are capable in low Earth orbit of seeing objects with sizes roughly around 10 centimeters and slightly lower. We are capable of seeing them, but that doesn't mean we're capable, by seeing them alone, that doesn't mean we're capable of predicting where they're going to be in time. And this is significant, this is important, because you might be thinking that a CubeSat has with a size at least of 10 centimeters for the one CubeSat, you might be thinking that such satellites do not need to relay any information because you're observable, but actually these entities require your assistance to tell to predict the position of your satellites in time. They need the orbital parameters of your object, and also being trackable also means that your satellite can be identified as your own. This is especially important when you have massive launches of objects, massive launches of CubeSats, and some of them might not be functioning upon launch. And it's quite difficult to identify who this object that is non-functioning belongs to. This is a clear liability issue. And I highly recommend you all to look at the document that I have provided in the slide. I will give it to you later. I highly recommend you to read it. It's a short document, about 4 pages, that provides a very good insight on the problem of this. So if you want to remain trackable, it is possible for you to incorporate in identification markers. So you can have either laser retroreflectors or unique signal markers such as transponders that would relay your information and orbit parameters. Now, I want to take the moment to advertise our software. So within ESA, we have the Drama software, which is free. You can download it on the link that I'm providing. And it's completely free, and it allows you to check for various things. It's very easy to use. It's quite intuitive. There's a user guide that goes along with it. It is really easy to pick up. And you can use it to check for the compliance of your mission. And it has different modules. So the different modules are ARES, the first module, which provides statistics related to collision events. So for your mission, it allows to see what's the annual collision probability, how many, the mean number of avoidance maneuvers you will have to perform given a risk threshold, and how much propellant you would require. Then there is MIDAS, which provides the flux of objects onto your object and the statistics related to the damage for your mission and the orbit you have selected. There is OSCAR, which is a module that is very useful for all other modules that I'm presenting here, because it allows you to model in a simplified way your spacecraft or your object, and it allows you to compute its randomly tumbling cross-sectional area. Now, the other modules require you to state for your spacecraft, they require you to state cross-sectional area. In general, we assume random tumbling of objects because this is the best guess we have, and it constitutes a somewhat reliable approach to computing the different things that you can do with the modules here. So you assume random tumbling of your object, you compute the cross-section, and with this value that you have obtained with CROC, you use it in other modules. And finally, you have SATA, which is a module that aims at analyzing the reentry of different parts and computing at the same time the risk related to your reentry. Again, I highly recommend you to download this because, first of all, well, you're entitled. You get it for free, and it's ESA approved. Now, I've mentioned a little bit what post-mission disposal is, what passivation is, what you need to do with according to the guidelines, but maybe this could be seen as an opportunity for the CubeSat community, because such technologies have there's a lack of spaceflight for such technologies, especially for smaller satellites, because at least on our part in ESA we have focused a lot on larger satellites, and we're gaining every year we're gaining more expertise on how to have a more sustainable behavior for our missions. But we have not focused extensively on smaller satellites such as CubeSats. So indeed, a lot of these post-mission and passivation devices have a lack of reliability, and that leads to an obvious reluctance to incorporate these devices because they have a mass and volume cost. It leads to higher cost for your mission, and if you implement it and go through all the hassle, you have to make sure that it will actually perform the action for which it is being designed. And as CubeSats are based on miniaturization of technologies, you have a tight mass budget, a tight volume budget. You need to find, it's an opportunity to maybe find technology that could help make a smart use of the budget that you have. For example, this is just an example. This is, again, I would like you to not take what I'm saying as ground truth, but just as a discussion. You have the tuna can that is present on some CubeSats when a specific deployer is used. This volume could be used to incorporate, for example, deorbiting technologies. It is also, CubeSats also have can also have the opportunity to help test and validate technologies to provide solution to the industry. So we believe that this is also an opportunity for you. And the reliability of these systems should be focused on. So for example, having fail-safe systems, having independent deorbiting systems, and you can look at there are various things that you can do with this, but it's important to focus on reliability, and we believe that CubeSats can help doing that. Also, CubeSats can contribute in other ways by providing data to support models that we are focusing on. So they can help characterize re-entries, they can help us look at the reliability, they can help assess the orbital traffic. There's many things that the CubeSat community can help us do. So we will look now at some technologies that have been looked at by various entities. For example, we have the first one is the drag sails. This has been focused on. This is a sail that is deployed to increase your exposed surface to the drag. So basically what it does is increasing your exposed area, which lowers your ballistic coefficient, which will in turn speed up your reentry, because the lower your ballistic coefficient, the higher the drag will be on your object. So increasing its surface will cause drag forces to be much more efficient on your object. So this is once this is deployed, this is fully passive, and it's quite efficient according to some studies for small satellites. But the surface area that you need grows significantly with the altitude of your satellite. So this should be considered. Again, these what we're presenting only represent what is being studied and being simulated by various entities. This does not represent a ground truth. Just because you implement a drag sail does not mean your mission will 100% be compliant, because this needs to be assessed in further detail. This needs to be researched more. Then there are solar sails. These are deployed to make use, instead of making use of the atmospheric drag at first, they make use of solar radiation pressure. So basically you have a reflective surface, a large reflective surface, much like drag sails. And this reflects the photons, which cause a force on the sail. So the typical method that has been seen in different studies as being very efficient is one that is passive. So letting your satellite remain as it is once the sail has been deployed. This would lead to an increase in eccentricity of your orbit instead of continuously decreasing your altitude like drag sails, until your perigee will be low enough that your satellite starts suffering highly from atmospheric drag. So from then on, your solar sail will behave much like a drag sail. This is quite attractive compared to drag sails for a little bit higher orbits, where drag sail where atmospheric drag starts to be less efficient. We saw earlier in one slide that atmospheric drag really is efficient for lower orbits. Once you start increasing the altitude, its efficiency is much lesser. But such sails, they have been related to a risk maybe, and risk on astronomical missions if they are widely implemented because of the disturbances that they can create. So this is also something that needs to be assessed if this is to be widely implemented by the community. Now, compared to the drag sail, where the surface area of the drag sail needed to be increased with altitude, this also needs to increase with your inclination. So it's very dependent on both your semi-major axis and your inclination. Then we have the electrodynamic tethers. These are long conductive cables that are deployed to collect electrons from from the surrounding plasma, and this in turn generates a current, and in turn a drag force, a Lorentz force. So basically, the movement of your object through the magnetic field will generate a current, and with this current, with the magnetic field, will result in a Lorentz force, which will, depending on the direction of the electric current, will decrease in time your altitude. Now, these need to be quite long cables to be efficient. So they can go from a few hundred meters to some kilometers. They require a strong magnetic field to work because, like I described, you need to have the movement of your spacecraft through the magnetic field. So you need to have a high density of plasma electrons, and for altitudes of about higher than above 2,000 kilometers, you get this starts to be less interesting, and also the efficiency of this system is lesser for higher inclinations. This needs to be considered. But still, it's attractive for higher orbits above 800 kilometers, where the magnetic field of the Earth is still can be an interesting approach compared to atmospheric drag. The lengths of these tether, I mentioned that it might be of some 100 to some kilometers, 200 meters to some kilometers, but the length of this tether depends on the ballistic coefficient of your spacecraft. So for larger objects that have high masses and perhaps the ballistic coefficient that is much higher, you need to have a longer tether. There's also been some studies to look at the consequences of failures of such tether, and they have found that having a double-stranded tether, so basically having two tethers parallel to each other, provides lower risk of losing your mission in case one of your tethers is severed. Now, propulsion at the end of life. So if you have propulsion on board, this could be used to deorbit your satellite, but your subsystem needs to be effectively designed for this function. This is not something that is improvised. Alternatively, it is possible to use independent add-on devices that you just put on your satellite, and these are independent. They will help deorbit your satellite with hopefully a high reliability. So, if it's present on board of your spacecraft and you do not use it for deorbiting maneuvers, these propulsive devices, this should be passivated. Because as we saw earlier, passivation is one of the major causes of fragmentations into orbit, and one of the main causes of a lot of debris flying around with these fragmentations. So what you need to do, what is recommended for you to do, is to either make safe, so you can add shielding to make sure that an explosion caused by your propulsion system will not cause a fragmentation of your spacecraft and not contribute to increasing the space debris environment. So this is making safe, and you need to actually demonstrate that this is made safe. Or you can deplete the stored energy. So by either you can vent, it's recommended to vent residual propellants, having the fuel valves open, venting all the pressure systems, and having pressure relief mechanisms that are activated. Now, about batteries, because propulsion was something that not all, even though there are changes, but the CubeSat community is not was until now not so much focused on propulsion, but batteries. This is relevant because batteries have been linked to some fragmentations, and this in recent years has also been proven to be true with the fragmentations caused by batteries exploding. So what should be observed? The recommendations on what should be observed for your battery to be safe is to discharge it as low as you can, avoid high temperatures even after end of life. So by designing your mission such that your battery will be protected from the harsh environment of space. And you should avoid recharging your battery, especially overcharging it. This is very important. Obviously, your passivation device, if you use one, should be kept in an acceptable environment to make sure that it is that it will remain reliable. So possible approaches. This is just some ideas that have been going around in recent years, and that have been quite some expertise on this for larger satellites, but not as much for smaller ones. But just possible approaches could be to use, for example, semiconductors to disconnect your batteries from the power sources and then discharge your battery as low as you can. And then the use of semiconductors to disconnect or short circuit your solar arrays. And alternatively, a possibility that was not really interesting for larger satellites could be the use of containment for your batteries. So basically, this relates to making safe. You would have your batteries within a box, or that would shield the rest of the spacecraft from potential fragmentations. So this is very important, and sadly, there is not much There is not much knowledge and expertise and experience for this in the community. But this is highly encouraged to look at it and look at solutions to make sure that your propulsive devices and your batteries will not have a risk of increasing the number of debris. So we went quite fast. I hope that I did not miss out on too much. But I would like to take a while to conclude and give you messages that I believe are the most important ones. So first off, I hope that I conveyed this message right. But the situation in LEO is really critical. The growing risk caused by space debris. There is some orbits that have a high likelihood, if the behavior keeps as is, there's a high likelihood that some of these orbits will become unusable in the future. And some of these are some of the most interesting orbits. So there is really an urgency caused by space debris, and this might well lead to stricter requirements coming in the future. So this might be more enforced in the future by different entities. As we saw also, and I hope I conveyed this message. I hope I did not convey it in too much of a critical way, because this is not the goal. But I just wanted to point out that CubeSats are a major contributor for the sustainability of space in years to come. Some of the efforts of larger satellites might in fact be irrelevant if CubeSats and other small satellites do not adopt them too. So this is really a global effort that needs the cooperation of everyone if we want to have a sustainable space. So the most important action that you can take to mitigate the growth of space debris environment is to guarantee that your spacecraft will re-enter the atmosphere within 25 years of your mission end, if you're capable of performing collision avoidance, or from your mission injection if you don't have any means of performing collision avoidance. So you could use for example, you could use and talk to some of our experts about if you have questions about the altitude and the type of orbit that you should have. You can use Drama, the software that I mentioned earlier, the free software that allows you to check for compliance and see for your orbit if you're capable, if you are compliant with the guidelines. Since reliability decreases with time, and currently there is not much verification and space flight for a lot of these post-mission disposal and passivation devices, a safe option is to inject your satellite in a naturally compliant orbit, which will make it compliant in any case by default. Stored energy can really cause and has been linked to a lot of fragmentations. So a significant number of such debris could be caused by the lack of passivation due to batteries and propulsion. And even this is true even for CubeSats. So this is relevant. This cannot be overlooked. So passivation should be performed. This is related to the next point with reliability of end-of-life measures. Reliability is crucial because, first of all, by standard, you should ensure, if you follow the standards and the guidelines, you should make sure that you follow the reliability requirements, but also for yourself. If you design a mission and decide to go through the trouble of actually designing your mission with stricter requirements due to the mass and volume budget that various devices could cost you, you want to make sure that it actually works. Another very important point, and please, I would really like to highlight the importance of this, is that tracking your satellite and relaying the information to collision avoidance entities is really important. Having a size of more than 10 centimeters and being actually observable is not enough. This is a real problem because there's this misconception that trackable and observable are the same things, but they are not. You should relay your information to be able to provide reliable estimations of the position of your spacecraft to the entities that will help ensure that no collisions occur. And also, to not finish on only a negative, to not be too negative about the future, we'd like to point out that space debris mitigation guidelines are in fact requirements, but they can also be seen as an opportunity to bring reliable technologies on the market because, as we said, there might be stricter requirements in the future because of the way the situation is going. Having space-proven devices could, in fact, be quite handy in the future if these start to become more recommended. So what's next? With this event, like we said, we tried to, we wanted to reach out to the community because we have quite some expertise with larger satellites, but this has not been the CubeSat community, which is a very important actor, and rightly so. This community has not been included as much as we would have liked to in the different issues related to space debris, and we would like to change that. So we'd like to advertise the CubeSat Industry Days that will occur here in ESTEC in the Netherlands. From the 4th of June to the 6th of June, there will be more information further on about this that you will be able to find, where these issues will be discussed. This is a very large and very major event in Europe, and we highly recommend you to take a look at it because you will see, you will learn about various things and be able to discuss with other experts from your field. You will talk about not only space debris, but a lot about CubeSats, but also we will take a look at these issues. So we have a couple of questions that you might be interested to ponder on until this event. So the first one is, how could the CubeSat community participate in making the future of space more sustainable? The second one, which is related to the first question, is how could we, as ESA, help you reach that goal? So if you would like to think on these questions and discuss with us, we invite you all to come and discuss with us in these CubeSat Industry Days, and we would like to hear what your opinion is. Now, as we said, this is the first time that we're doing an event in such a form with a live stream on YouTube. It's the first time that we're really involving the CubeSat community and targeting you to try to raise awareness. So we're well aware that there might be there might be recommendations and changes that we could do to improve. So we're very, very interested in your feedback. If you have anything to say, so questions, suggestions, remarks, criticisms, if they can be constructive is nice. We're very interested to hear about your feedback. So please feel free to contact us at the address that is here, so cleanspace@esa.int. Again, this presentation will be provided to you in a while, so you will have access to all this information. And we also recommend you to visit our blog, where there is a lot of information about the other disciplines too, such as eco-design, active debris removal, and other activities that you might be interested in learning more about that we have not had time to assess today. You can also follow us on LinkedIn and follow us on Twitter, where we provide a lot of the most important information. So now, first of all, thank you all for your attention. We really appreciate the interest that has been here so far. And we'd like to take a moment to answer some questions. So if some of my colleagues have gathered questions, we can take a look at them now. So, okay. Yeah. So has there been questions that you would like to?
Hey, so yes, there was quite a lot of interaction online, so this is very positive. Thanks for your questions, and we will be, as I said, trying to answer also afterwards to whatever comments. You can still comment online. Just to summarize a little bit the inputs we got, there were some questions or a lot of questions regarding how to track from ground. What we are doing also for larger satellites is trying to include passive means that help the deorbit, the tracking from ground. Because actually after the end of life and keeping something autonomous working for another 25 years is very hard to guarantee. So in this sense, there are systems on ground that are today already tracking the objects that are in space, as Njord said, bigger than a certain limit, but these are the ones we can track at the moment. There could be other technologies, so we are not saying that these are the only ones, but just to tell you more or less the direction we have been going, but for larger satellites, maybe for smaller ones, we want to consider something different. Another point that was quite a lot discussed was the 25 years and whether this should be reduced in the future and what can contribute to this. Also working on the ballistic coefficient or in other aspects. So the requirement now is quite clear and tries to be very simple to tell you the orbital lifetime has to be reduced to a maximum of 25 years after the end of life, or if you don't have collision avoidance maneuver capabilities, then it should be counting from the beginning of the life of the lifetime. So actually, this is already guaranteeing quite a lot of mitigation of the number of debris in orbit, because as Njord showed, the moment you go to higher orbits where you have to stay longer, and if you fail there, if you stay there after the end of life, then the time you spend in space will be growing exponentially, and the time any fragments that will be generated in a fragmentation event or in a collision will also stay exponentially longer. So basically this aspect, the 25 years, is already bringing quite good results. Of course, whatever can be done to reduce it is always helpful. And I cannot say from what will be the evolution of the requirements. I think it can change, but at the moment, this value is already bringing a lot of positive impact to comply with this. Another point that was discussed was to deal with what we call design for removal, so to have some features on board that could help a spacecraft to be removed from orbit. At the moment, what we want, or what is in the guidelines, is that we need to have a post-mission disposal operations and functions reliability or probability of success that has to be high, higher than 0.9 according to the models to make the environment sustainable. And this can indeed be even low if we consider the future evolution of the debris environment. But at the moment, this is a value that, as I say, already gives also a lot of benefit. So whatever means are put on board to have an external system to remove you would have also to prove that is compatible with these figures. And yes, it's something we are looking at as well in ESA for larger satellites to include some features, but also can be seen as a backup in case your satellite fails in orbit. Now, the figure to keep in mind is that we need a success rate that is quite high, and this has to be proven to allow your satellite to be in agreement with these guidelines when you design it. So this is also conditioning you're taking and takes a part on selecting the method you put on board. I don't know if there are other questions that came in the meanwhile.
One we just got is from Marco. One of the most promising technologies for debris avoidance for CubeSats.
For debris avoidance, you mean collision avoidance maneuvers?
Yeah, I assume so, yeah.
So it seems to be a question that also came up quite a lot regarding the collision avoidance maneuvers. In the end, you need propulsive means or some sort of way to perform some delta V in space. It's very hard to imagine that you could do that using drag or changing the attitude of your satellite, because you have really quite a lot of uncertainty on the point of interception and the probability of having a collision. So you have to avoid a volume that is rather high. So you need, in principle, to have propulsion on board to be able to do collision avoidance maneuver. I don't know if there were other questions coming in.
Maybe if you want to ask them for more.
Yes, if you have any other questions, we still have some time here, so we can still try to answer.
2 seconds.
Okay, so I think we will actually close the webinar now. This will be available online. Maybe Njord can give you some more details on that.
Yes, this will be saved on the YouTube channel of ESA. So I can also provide the link again if some people have trouble finding it. I will provide the link along with the presentation for you to be able to see it again in the future if you're interested in doing so.
Yes, and it would be very good to keep exchanging. So if you have questions, even when you see this video afterwards or you share it, if you get questions, don't hesitate to add it in the YouTube channel and we'll try to answer as soon as we can. Also feedback to know if this was a useful format so that we can also decide to do it more in the future or not. Or if you have specific topics you would like to see addressed, let us know. Otherwise, then thank you.
Thank you very much.
Thank you, Njord, for preparing all of this and organizing.
Thank you very much for your time. We appreciate your interest and we look forward to more interactions in the future with you. So,
goodbye.
Bye.